like and leave a heart. Please.
There we go. Hello, everybody, and welcome to the FDIR Locksmith Show. I'm your host, David Gibson, where we are unlocking the secrets to success in the oil and gas industry. One interview, one technical presentation, and one technical screw up at a time. Thank you guys all so much for being here with us on this amazing Friday. We've had a last Friday off for Good Friday. Next week we'll have off again. Sorry, guys, they're trying to throw a couple of consistent weeks here together, but next weekend is race weekend. The I don't know, the infamous Octane / altitude racing team will be taking on Hallett next weekend. So really excited about that one. But we have today's show. We're here this Friday. Guys, let me know where you're watching from. Love to be able to give you a shout out here on the show, as well as today is brought to you by #Rig Reports. Special thanks to the guys over at Mi4 and Rig Reports for sponsoring this show. We're gonna have some cool giveaways to be able to throw out there to you guys here pretty quick. Maybe one of these days, I'm just looking at this. Maybe one of these days I'll do these again. We'll throw out some chocolate drill bits or the Gibson Reports cookies. Those are real cookies that we made. That was even before all the AI stuff took off. But yeah. Thank you guys for being here this amazing Friday. Oops, sorry, got to put that one back on there. There we go. All right, got a couple of people tuning in here. All right. Oh, good morning, Mr. Keith Stelter, tuning in from the Permian. Thanks for being here, sir. He's out there doing the, I think it's the Stelter Initiative, cleaning up West Texas. Tracy, you do me a favor and hit the autofocus button there. Can't quite tell where I'm supposed to be standing. I keep seeing like out of focus. Also got Colin tuning in from Aberdeen. Thank you for being here, sir. Do appreciate it. And Zuar tuning in from Norway. Got the international audience going this weekend. See if anybody from Houston jumps in there here pretty soon. All right, guys. As we're waiting. Oh, there we go. Mr. Can't believe it took him all the way till the fourth comment to be able to join in. But Mr. John DeWart watching in already on top of it, putting in #Rig Reports. Robin McMillan says, more cookies, please. Yes, I mean, we could do it. I've got the 3D molds for these. We've got the 3D molds. We'll make some cookies again. I'll put that on my to-do list. In and amongst like a million other things that are on the to-do list. So yeah, John says, good morning from Elkhart Lake, Wisconsin. Music is in the air. As World Racing League qualify 8-hour endurance race Saturday and 7-hour race Sunday. That's what I'm talking about. That sounds like fun. All right, Mr. Blaine tuning in from Spring, Texas. Thanks for being here. Talal, our sponsor. Thanks for tuning in, sir. Do appreciate it. Had a great meeting with him the other day. Actually met with him after my IADC presentation that I did the other day. It was a lot of fun. All right, thanks, Keith. All right, guys, let's do let me get out of order on this here, guys. Okay, first of all, yes, put in #Rig Reports, right? Put that one in for your chance to be able to win a 3D printed drill bit. And this is the coolest thing, right? This is some really custom stuff. So this is Talal makes these, right? So it won't say David Gibson on it. It'll say your name, right? And then on the back of it says rigreports.com. So yeah, put in #Rig Reports for your chance to be able to win one of these and one of the 3D printed drill bits. So, quick word from our sponsor, and then we will jump on to the show here. Hello from Brittany. Okay, sounds good. Not really sure about it, but Rug Reports. No, Rig Reports. That's all right. Guys. All right. I'll do the quick little commercial real quick, and we'll be right back with our guest of the day. All right, quick break to tell you guys about Rig Reports from Mi4. They are sponsoring the show today, and honestly, their daily operations app for operators and consultants is something you should know about. Picture this: no more juggling Excel spreadsheets, endless emails, or paper reports. Rig Reports takes all that mess and replaces it with a fully digital automated system. That means everything is faster, more accurate, and way more efficient. You get real-time access to reports and analytics, so decisions don't have to wait. You can act immediately, whether it's reviewing a job or approving an invoice that shows up months later. It even makes look backs a breeze. And the best part is it's so intuitive that most users don't need training to get started. If you're a consultant, and you'll love this, each of your clients gets their own database and you can switch between them without skipping a beat. Go to rigreports.com to learn more and schedule a demo. Seriously, guys, it's worth taking a look at. Not just yet. Wait till after the show. Then go take a look. All right. Very serious. Everybody out there, get your pen and paper ready, or whatever note-taking app it is that you guys use. There we go. Whatever note-taking app it is that you use, get it ready. We've got an absolutely amazing guest. One of the best in the industry, was drilling engineer of the year 2024, 2023. I can't quite remember. But like I said, absolutely amazing guest. Happy to have him here on the show, Mr. Eric Cayeux. Eric, thank you for being here.
Thank you very much. Yes, and thank you for inviting me on the show, David.
I know you've got a great presentation. It might be a little bit longer, but I still want to be able to give you the opportunity. For those that don't know who you are, give us a quick introduction.
Well, I've started my career actually outside the oil industry because I was educated as a civil engineer. So I started to work with road design and bridge design. But then I moved to Norway because of love and because my wife is Norwegian. And then I started to work with the oil industry. So I worked 18 years in the industry, and then 20 years ago I moved to the research part and started to work with NORCE, the Norwegian Research Centre. And I've been enjoying all the day with NORCE since I've started, and a lot of fun with research and trying to find also details about the drilling process.
Excellent. Well, I'll go ahead and let you get started. I'll go ahead and put this up on the screen, and then I'll switch these two so you're at the top and let you take it away.
Very good. Thank you. So what I thought I would tell you today for the show is the journey from mathematical models of the drilling process toward autonomous drilling. So it's a long journey, so it's a long presentation, so I hope you will bear with me until the end. But okay, so this is the outline of my presentation. I will start with some motivation, then I will talk about modeling of the drilling process, then I will continue with how we can do early detection of deterioration of drilling problems, and then I will carry on with the functions for drilling automations, which is more like a assistance function. And then I will sketch what we have started to do towards autonomous drilling before taking some conclusions. So for the introduction and the motivation, so I like just to focus the fact actually that in drilling there are many different aspects. There are target selections and designing of wellbore architecture and all these kind of things. This presentation or this talk for today will be focusing only on well construction, so the operational part of it, and the rest can be left for another topic. Oh wow, that's a bit messy slide, but the point, okay. The point of this slide is just to say that actually there are most of the software which is used out there is using steady-state models, and steady-state models are not really well adapted to actual drilling operations. just because actually there is a lot of transient periods. And as you can see here, during this friction test, steady state model, which is shown in green curves, will jump right from free rotating weight to pickup weight, and then just jump to a slack of weight, while actually the measured values are changing slowly. And this is reflected by the fact that there are some transient effects that are happening. This is the point also with drilling operations is that there are quite often drilling incidents, and these drilling incidents are causing delays. And the more we try to avoid those incidents, the better it is actually for the efficiency of the drilling operation. So the other things is that actually there is a lack of consistency. If you see here a set of friction tests which has been executed by drillers, you can see that there is a lot of variations in this series of friction tests, even though they are made in the same operation. And that is not very good actually to extract information out of the drilling operation. And probably some of those friction tests are not efficient, and some others are not capturing actually what should have been capturing. So the question that we have been working at the research center is, can we do a mathematical modeling of the drilling process, which is having enough details such that we can actually reproduce what is observed. And therefore we can use that models actually for providing inputs during the drilling operation. So here you see the drilling operation offshore of Norway, where there is heave. You can see that when we are drilling, there are variations of the block position because of the imperfection of the heave compensation system, and there are very large variations in the weight on bit. And even though these variations are quite complex and affecting the drilling process, the modeled values are getting very close actually to the actual values which are measured. So that shows that it is possible to process actually this drilling process modeling at a very good level of details, which can match actually reality. The other things that we would like to address is whether we can detect abnormal situations before any drilling incidents has happened. Because if we can detect that before the incidents has happened, so we can take proactive actions and we can cure the problem before it causes any delays. So here the graph that you can see shows actually that there are too few cuttings coming to the surface. The expected values for the volume of cuttings coming to the surface is displayed in the green curve on the right-hand side, and the actual volume of cuttings which is appearing at the surface is on the blue curve. And you see that this lack of cuttings can definitely cause some troubles very quickly on the drilling operation, because you can get into back-off situations due to the poor opening. And then the ideal situation is that actually we can control the drilling rig and perform assistance for the drilling operations, and such that we can get better consistency. You see here friction tests which are done automatically by an automation system, and you see that they're much more consistent than the one we saw performed by the driller. And you can also see that these friction tests which are done automatically are changing in lengths to account for the fact that actually the elasticity of the string is changing, and because of this change of elasticity, so we need to have longer friction tests actually to account for the fact that it would take times before the bits start to move when we are moving up and when we are moving down. So we can introduce into this automation information which is optimizing the performance and accounting for the current context. So how can we achieve that? How can we do all those questions? How can we answer all those questions that are listed there? So first we need to start with trying to model the drilling process as precisely as possible. This is strange because there are quite a few things which are jumping over. So, but okay, that's the way it is with the presentation. So, so the point is that we have a system which is a drilling process, which is in blue, and this process has a certain number of inputs. That's actual velocity, the rotational velocity, the flow rating, what kind of weight and bit we have, and so on, the density, the temperature. And that will give outputs. And what we want to do is to have what is often referred as a digital twin, a drilling process model, which takes the same inputs and which provide modeled outputs, which are as close as possible to the true system outputs. And one of the first things that we need to consider is that actually in drilling operations, so we have very large gradients of temperature between the surface and the downhole conditions. And therefore, we need to have some kind of modeling of the heat transfer during the drilling process. And this is done by some heat transfer model, which calculates actually the temperature both of the fluid inside the string, inside the temperature of the string, the temperature inside the fluid in the annulus, and also everywhere into the casings and formations. And this allows actually to calculate what will be the temperature conditions everywhere into the system. Now the sources for for this calculation is coming from different conditions. So there is the advection of fluid into the transport. It should have been an animation, but I see that the animations are not working on the display. So sorry about that. And there is heat which is generated by the pressure losses, because these pressure losses are converted to heat generation. And there is also heat provided by the mechanical friction of the stress string against the borehole. And all these change the conditions of the drilling operation. And if the animation would have been working, so you would have seen that actually that for the first 6 hours of starting the drilling operation with circulation and rotation. So there is a drastic change in the temperature conditions into the well. So you see that we had the model which has to do with drilling heat transfer. We need to have a model for drilling hydraulic to calculate the pressure losses. We need to have a model for drill string mechanics to calculate the friction. And these are actually giving inputs actually for the drilling heat transfer calculation. So there are some mutual interactions between those different models. And if we carry on, so we can see that actually the drilling fluids is a mix of different components, and each of those components has different PVT behavior and specific heat capacity and thermal conductivity. And each of those values depends on both the temperature and the pressure conditions. So that will influence actually the calculations for hydraulics and mechanics, because actually the change of heat actually will impact actually the calculations for drilling hydraulics and drill string mechanics. In addition, we are transporting cuttings. Those cuttings change the composition of the fluid. because of the solid that they are transported. And if the animation had been working, you would have seen actually that both the mass density and the specific heat capacity and the thermal conductivity would be impacted by the cuttings which are transported through the drilling process. And conversely, this change of the thermophysical properties of the fluid impact also the heat transfer that we have into the drilling process. And then we can continue with the pressure losses and the impact of the temperature and pressure conditions on the rheological behavior of fluids. And there again, so we have strong variations of the rheological behavior as a function of pressure and temperature. So you see the rheogram showing the shear stress as a function of the shear rate for a specific fluid at different temperature and pressures in the top graph. And you see that the rheological behavior is very different when you are working at cold conditions than when you are working at very hot conditions. So this impact also the pressure loss calculations. And as already mentioned, so cuttings being transported also impact actually the rheological behavior. And you can see here on the lower graph that actually the rheological behavior at the same conditions of temperature and pressure is varying a lot depending of how many cuttings we have into the fluid. And all this has been measured with scientific rheometers for getting accurate results. So this is reality, this is not synthetic things. Now, considering this, we have an interaction between the heat transfer and the material transport on the drilling hydraulic. And if the animation had been working, so you would have seen that actually that during the drilling process and when we are producing the cuttings, so the rheological behavior of the fluid is very different in the annulus when it is getting starting to transport actually cuttings. But you can see on this fixed picture that you see here that actually the rheological behavior is different at the surface and compared to the bottom hole. That's the two right hand side graphs, which shows the FAN 35 values for 3, 6, 30, 60, and up to 600 RPM with the color codes, which is following these rainbow colors. And you see that the rheological behavior is very different, both inside the string and inside the annulus, because of the change of difference of pressure and also the change of temperature. So we have start to have quite a few correlations between the drilling hydraulic, the drill string mechanics, the material transport, the drilling heat transfer. And then we can detail more what happens with the cuttings transport. So the movement of cuttings particles is dependent on the both the movement of the drilling fluid, and the movement of the drilling fluid is imposed by the flow rate and also by the rotational displacement or the displacement of the drill string. So the particles are moving in a complex path depending of this fluid velocity field that we have into the annulus. And they can get transported directly if they get catched into the high velocity field, which is usually on the high side. But if some particles may be deposited on the low side, and others may be transported simply by erosion of the cuttings bed, if there is a cuttings bed which is forming, and if the drilling conditions are changing, so maybe some of the cuttings into a cuttings bed get resuspended and get transported in on the high fluid velocity field in the high side. So there is a lot of variations, a lot of which can happen during the drilling operations, and the cuttings transport is a very transient phenomenon. So again, there is no animation, but the point was to show that actually when we do a connection, so actually the cuttings which were transported in suspension may go back into a cuttings bed during the connection time, because in this horizontal well, actually the distance for the cuttings to sediment is very short. And then when we restart the circulation, if we don't have the rotation, actually this cuttings bed doesn't disappear instantly. It takes time, and actually it's only when we have the rotation of the string that we can start to lift the cuttings which are on the low side and towards the high side that the cuttings bed disappear. So again, at every connections, you may have quite a lot of variations of positions of the cuttings during the drilling operation. And then also the cuttings get grinded when they are transported. Some of the cuttings particles are transported on the high side, and they don't get trapped below tool joints along the tree string. But some others may be more unfortunate and get just trapped between the tool joints and the borehole. And because of the rotation, they get grinded. And depending of how many times actually those particles are grinded, so some particles may never be grinded at all, and they will come to the surface as they have been produced by the bit, relatively large. And some others may be more unlucky and get grinded many times, and they get smaller and smaller and smaller. And that's what we observe at the shakers, at the level of the shaker, is that actually we have a large distribution of cuttings particle size which arrives there. And that may depend on the size and the duration of the operation. So the cutting size distribution for 17.5 operation is different from the particle size distribution for 12-quarter or 8.5 section, and depends also on the energy which is provided to the rotation for rotating the string. So the more rotation you put, so the more grinding you can get also. But if you have a good transport of cuttings, actually you get less cuttings particles being trapped below the tool joint. So all this is very linked together. And also something that our models and observations or measurements have shown is that actually we can see that vibration, so dynamic tracing modeling, can be influenced by cuttings particles. So we have seen that actually when the flow rate is reduced, so we can get into stick-slip situation, even in off-bottom conditions, while we are transporting cuttings. And when we start again, regain back actually the flow rate to a larger value, so these stick-slip conditions disappear after some time. So there is a direct connection between material transport and tree string vibration effects. And talking about tree string vibration, so an important thing that we learned is that there is a transition between static friction and kinetic friction. And this transition between static and kinetic friction is very important because it creates some specific conditions for how the tree string behaves when we start rotation, when we change directions, and all these kind of things. So we use a Ullrigg model for the transitions between static and kinetic friction. We also solve the problems when we are in static conditions of what is the actual friction force, which is actually undefined from the friction equation, but which is defined by the equilibrium of the string. And this is quite important too. keep actually the tree string non-moving when we are in static conditions. The other things we've noticed is actually that when there is rotation or when there is movement, sorry, the kinetic friction is more or less constant regardless of the direction. The friction force is always opposite to the displacement vector. And that means actually that there is an easy path between the movement, the actual movement and the tangential movement. So you can actually easily move from axial displacement to torsional displacement because the kinetic friction magnitude is more or less constant or independent of the movement itself. And this has an impact. So the animation would have shown actually that when we start rotating, so we rotate the string and there is almost no vibration. And then we start to move axially the tree string. And when we start to move axially the tree string, so the rotational speed start to oscillate. We don't get stick slip, but we get large amplitude oscillations. And this is due to the change of axial direction. So exemplifying what I'm saying, that actually that there is an easy path between axial and torsional in terms for the displacement in terms of the mechanical friction. And then there is hydraulic forces applying on top of the tree string. These hydraulic forces impact actually the forces, especially around the tool joints, but anywhere you have change of diameter. And that can lead actually to very strange behaviors, like, for example, into this reciprocation, which is shown here, where we are reaming up and then rotating off bottom and then reaming down. You can see that when you are reaming up, the torsional oscillations damped very fast, actually faster than when you are rotating off bottom without actual movement, which is the middle part of this graph. But when you are reaming down, actually this torsional oscillations start to amplify and gets into stick slip conditions actually. And this has been verified by measurements made downhole, that actually this the direction of movement because of pressure effects on the string can induce actually larger torsional oscillations than when you are moving upward, for example. So there is again a direct interaction between trailing hydraulic and tree string mechanics. And as you can see here now from this graph, the part actually where we have the description of the hydraulic model and the tree string mechanics and the drilling heat transfer and the material transport, there is complete interaction between all four modules. So you can't consider the one independently of the others. Each of them are influencing the others completely. So that is really important to consider all those aspects at the same time, and considering also the mutual interactions between those different models. And that gives
Eric,
actually the, yep.
I'll pause you real quick. Is there a possibility you can share your screen with the presentation, so then maybe the animations will be able to come through?
Yeah, I can present. I can. So how can I share? If I click on present.
So present, and then at the very bottom of that list, it
share
should
screen.
say share screen. Yep.
Okay. Yeah. Share screen. Yes. And can I share the whole screen? Entire screen. Yes, I see that. Share. Nothing happens.
Let me remove.
Okay, yeah. So no, that's me. Yeah. No,
Okay.
I think I'm sharing.
There we go.
Yes. Okay, good. Let me see if I take this presentation. Yes. Okay. Yeah. And then I will go to, yes, I was there. And if I do like that, yes. Do you see the
Yes.
presentation? Yes. And do you see the animation? No.
Let's see here.
Do you see the graph which is evolving here?
Yes, everything's going. Let me just, there we go. We can make it a little bit bigger.
Okay.
Yeah, so everything's working now. There we go.
Okay, good. That's good. So what we've seen is actually that by having those 4 different models, drilling hydraulics, drilling mechanics, drilling heat transfer, material transport, really tightly connected together, so we can calculate the complete internal state of the system. And the complete internal state of the system is shown with these different graphs. There is the pressure, the temperature, the density, the fluid velocity, the cuttings proportion, cuttings bed height, the rheological behavior, side forces, tension, so plenty of things. But that's the total internal state. And this internal state is calculated. So with the model that we have developed, it's calculated every 10 milliseconds. And it's updated compared to the inputs that we give to the drilling process. So that sounds good. And we do manage to reproduce very well, actually, the output of the system, where it is measured. So, for example, the standby pressure and the hook load and all these kind of things. But there is an additional complexity, and this additional complexity is that actually what we measure with sensors is not necessarily the same thing as what happens in the physics. And I'd like to illustrate that with the pit volume. If you think about the flow rate in and flow rate out, and you want to detect a kick or things like that, so you want to know what is the flow rate out of the well. And the point here is actually before you get a change into the volume of the pit, that will happen after the fluid has been transported through the flow lines, has been separated with, or the cuttings has been separated from the fluid as the shell shakers, and the remaining fluids is getting back into the pit. And a lot of people are talking about wellbore briefing and other things, but there may be wellbore briefing, but most of it is explained by 2 things: compressibility of the fluid inside the well, and the retention of fluid into the surface installation, transport of fluid. And you can see here also we model actually the flow of fluid into the open channel for the flow lines, and the separations of the cuttings into the shell shakers. And you see how much delay there is and how much retention of fluid there is into this system. That explains actually why we have a deficit of volume when we have started the circulation, and when we have a gain of volume when we stop circulation, because we regain back actually this fluid which was retained into the surface installation system. And in addition, there is some fluid which has been compressed into the well, which is released when the circulation is stopped. So we really need to also model the sensors. There are many more sensors that we have modeled, but if you don't model the sensors, so you get into troubles with understanding the measurements which are made, which are not exactly the one of the internal state of the drilling process. And another thing I would like to attract attention is even things which are very well accepted and well used, actually the FAN 35 rheometer values. You should be aware that actually that they are not correct, because actually the FAN 35 rheometer give you a translation of torque into shear stress, assuming that actually the fluid is Newtonian. And as we don't use Newtonian fluids, actually this conversion is wrong. And the same, actually, the rotational speed of the fan 35 remeter is usually converted into shear rate. And this conversion from rotational speed to shear rate is using actually Newtonian assumption, which is not correct for our fluid. And this is exemplified here with this. So we use the fan 35 remeter with two configurations for the bulb, R1B1 and R1B2. That's the same fluid. So the purple circles here are the measurements which are made with the R1B1, the traditional one that we use in the at the field. And then the green measurements is the same fluid measured with the R1B2. And as you can see, the two curves are completely different. And actually, if we apply the corrections from the correct corrections for conversions of shear for shear rate and shear stress, so you see that actually obtain almost the same curve for the true one, and which is totally different from the one which were actually originally measured. So there is a lot of possible traps in the data that we collect, and we need to be aware of that, and we always need to question whether there are things that we assume to be correct, which is not correct. So this is an important lesson through all the work that we have done on understanding drilling operations. So how can we use that digital twin to detect early deteriorations of drilling conditions? The first thing is we need to work on uncertainty. It is an essential thing. Everyone who has gone through a lecture on physics, the first lecture or the first thing you learn is that actually no values should be given without the uncertainty associated with the value. And in drilling, we tend to forget about this uncertainty, and maybe we don't like it, but it is still there, and actually this uncertainty is very large in many cases. And this impacts quite a lot, actually, the quality of the work we can do. So I would just like to illustrate the fact, actually, that even the density of the fluid is somewhat quite uncertain because first it's measured with instruments which are not very precise, but also it depends on pressure and temperature, as I explained earlier. And usually this PVT behavior that characterize actually this pressure and temperature dependence is not measured anywhere. So we rely on models, and those models are, again, not completely correct. So they have some uncertainties. And that can give actually quite large differences in estimations of hydrostatic pressures at deeper and deeper. And when you have geopressure windows which are in the region of 10 or 15 bars in some regions, that as we have somewhere in Norway, if you have such an uncertainty of plus minus 5 bars just on the hydrostatic pressure because of the uncertainty of the density at different conditions of temperature and temperature, so that's quite dramatic. The measurements of rheology, as I explained, first needs to be corrected for all those non-Newtonian effects, but depending on how you read your rheometer, especially if you use mechanical rheometer like the fan 35, so you may get in different results. And that has to do with thixotropic effects into fluids. And you need to wait actually quite long before actually the measurements are stabilized, and because of static friction into the mechanical rheometers, usually you can't see actually those effects. You really need to go to a scientific rheometer to understand how important those effects are. And that means actually that the same fluid measured by different people can give different results simply because of those thixotropic effects which are there. And then when you want to use that rheological behavior at different conditions of pressure and temperature. So you need to use a model to extrapolate, and again, the extrapolation from the model gives some uncertainties. So as you see here from this graph, actually the measurements are shown in blue. The extrapolations are made using models, but they are associated also with the P50 and the P95 margins actually for the uncertainty on these measurements, using actually the measurements, the models that is used to extrapolate for different conditions of pressure and temperature. And then, of course, if we have cuttings being transported, the rheological behavior change, as I mentioned earlier. And this also is impact actually the uncertainty of the calculation for pressure drops. So you see here the pressure drops calculated with 0% of cuttings. This is a blue curve. You see that there is a probability distribution because actually of the uncertainty that I mentioned earlier, both in density and in rheological behavior. And this rheological or this pressure drop that we calculate with a certain proportion of cuttings being transported is, of course, larger because the rheological behavior gets more thicker. But also because its probability distribution is larger also because of uncertainties that we have on the impact of cuttings presence on the rheological behavior. So some of the information is uncertain, or not necessarily uncertain, but ill-defined, and therefore we also need to adjust actually the calculations that we have with what is measured. But this information may not change during the drilling operation. So, for example, the linear weight of drill pipes, the exact internal diameter of drill pipes may not be known exactly at tenths of a millimeter accuracy. And that impacts actually quite a lot pressure losses inside the string. And half a kilo per meter error on the linear weight of drill pipes also may impact quite a lot the free rotating weight. So we need to do some corrections. This has been done for some time in our research center. I've seen that our colleagues from UT Austin presented a paper at the drilling conference in March, going in that same direction. So this is what we call global optimization, where we make sure that actually the data are consistent throughout all the observations that we have available. So what we have is we have this system, we have the sensors, we have this digital twin with the current state evaluation and the evaluation of the sensors to be able to do that. And then we utilize the measurements into this global calibration mechanisms to make sure that we can calibrate some of those parameters so that they are correct. And then when this is done, actually, we get a very good match of the models and after modeling of the sensor outputs with the measurements. But not all the parameters are not changing through time. There are some parameters which change with time, like, for example, the mechanical friction or the hydraulic friction. So it's not that the friction is changing, it's that there are some additional effects which are not accounted by the model, which influence actually the results. So there we use local calibration loops, which make sure that we calibrate actually the model so that it fits actually with the measurements. And you can see here with this friction test, with a free rotating weight period, and then stopping the rotation, and then doing a pickup, and then a slack off. The model matched very, very well, actually, the observation compared to the first slide that I presented, where we were using this steady state model. You see that the transient model have a very, very good match. And it also accounts for the fact actually that the driller has forgotten to zero torque the top drive when he has stopped actually the rotation. And therefore there is still twisting of the drill string while we are doing this pickup. And actually, even when we are finished with this slack off, actually the drill string is still twisted inside the well, which means actually that we have not yet measured neither the true pickup weight or slack off weight for this this test. But the calibration of the friction factor has been able to be done, even in these strange conditions. And therefore, we can add, in addition to the global calibration loop on top of the digital twin, these calibrations, these local calibrations for a certain number of parameters, like the mechanical, hydraulic, formation strength, and bit accuracy. So with that, we've got actually a system which can tell us what is expected, but with the uncertainty. So the uncertainty on the international state is evaluated by the system. Everything is based on uncertainty. You see here that how the system calculates at an instant t what will be the pressure inside the string, what will be the annulus pressure in equivalent mud weight, what would be the torque along the string, and what is the tension along the string, with the uncertainty associated with the calculation. And depending on the quality of the calibration which has been made, the global and the local calibrations, this uncertainty may be small or large. So therefore, there is also a reflection through this uncertainty of the quality of the work which has been done for the calibration. And therefore, give us more or less confidence on any potential detections of abnormal conditions. So what happens if you see that the friction was relatively steady and then suddenly start to increase like that? You see again that this friction has been calculated with some uncertainty, which is this blue, light blue band, which is indicating the P15 and the P85 margins for the calculations of the uncertainty of the friction. But then you see that actually you are deviating so much actually that you are very outside the initial conditions that you had here. So probably there is something which is deteriorating into the hole, and this is a good indication that maybe there is, it is time actually to think about what is happening there. Another thing is you can see here from this animation that sometimes actually so you see here this gauge which is showing the hook load. There is a needle, and then there are two triangles in green, and these are following actually the needle, but sometimes the needle is going much below the lowest triangle. So those two triangles are representing the uncertainty that we have on the measurements that we have for the hook load, or the estimation of the hook load. And you see that sometimes it's going above, sometimes it's going below. And that's indicating some set down weights and overpulls. So that is also a way to detect actually abnormal conditions, is that you have some small deviations compared to what is expected. And then I need to change my presentation to the second one. Okay, here. Yep.
Eric, try to actually go back to redo it. When you do the present and then it says share screen, instead of entire screen, hit window. That might make it so, because there was a lot of the blank space on either side there.
Okay. So let me try to find.
There's some details in there. I want to make sure that everybody's able to see.
Sure. So I go to present and then share screen and share.
We do have one question as you're pulling that up. Are references used to develop the model available in public domain?
Good question. So many of the models that I've been talking now are not available in the public domain, but we are working on transient torque and drag model that is actually being developed right now, that will be put in the public domain in the open source drilling community site. That will be available towards the end of the year. And it's very fast transient torque and drag with axial, torsional, and lateral modeling. So hopefully that can be useful for some people. That's developed in C#. That will be packaged into a microservice, and everyone can use it. No royalties, no stuff. And hopefully that can be a reference for people afterward. As a reference also, we have a simulator which is available online. You don't get the source code, but you can use the simulator. And it's called Open Lab Drilling. So if you search for Open Lab Drilling, so you will get access to that, and you can run the simulator for half an hour at a time for free with a Google account or something like that. If you want to run simulations longer than half an hour, so you need to pay. But, okay, you can do a lot of simulations with which are lasting less than half an hour. Going back to the questions of detecting abnormal conditions. So here is an animation which is showing actually the situation where we have some poor cuttings, some poor transport of cuttings. You see here the
Eric, can you make that full screen?
It is full screen.
On the presentation or in the PowerPoint portion. It's yes, in the PowerPoint view.
Is it? Okay. Oh. Because I'm doing the slideshow.
Yes.
And when I do slideshow, you don't see the slideshow?
No, it's still in the previous view.
Ah. Okay.
Maybe reader view.
Reader view.
Should be the next one over from there.
Slideshow. View. Reading view. Okay. Still. That's because my screen is very large.
Oh, that's okay. That's okay. It'll still work. I'll just I'll set it larger and then put you down at the bottom.
Sorry. I don't need to be on the screen. So
no. It's okay. All right. I'll let you keep going.
Yeah. So basically, what we see in this operation is we are drilling and we are circulating, and you see the blue curve here in this standpipe pressure track. Is the actual standpipe pressure which is measured. The green curve is showing the one which is calculated by the model. And you have a band of green, which is showing actually the uncertainty on those calculations that we are doing. And as you can see here also, there are some periods where actually the actual standpipe pressure is slightly larger than what is expected. And then it returns back to normal conditions. But it's more or less stays within the margins of the uncertainty. But this translates into some standard deviation in the distance between the actual standpipe pressure and the true and the estimated standpipe pressure. And this can be an indication, if this standard deviation is changing, that actually there are some changes in the downhole conditions. There we have another conditions, which is also showing that it can be used. these weak symptoms that we are talking about. Here is an operation. You see here again, the needle is showing the standby pressure, and the two green triangles are showing the margins that should be accepted. And you see that actually we are overpassing the margins with some high pressures, spikes. And this is impacted in actually the drilling operation and the driller peak of bottom, because you see that there are some back of tendencies. And at the end, actually, just stop the pump because actually there is more and more back of tendencies coming. So that illustrates that actually we can use those this calibrated digital twin with uncertainty. I really insist on the fact that this uncertainty is really crucial to be able to detect these weak symptoms. When we start to deviate outside the uncertainty of the model, then we can start to say that there are weak symptoms of deviations from normality, and therefore these weak symptoms can be used actually for taking decisions. So this is not only research, so this has been used in the North Sea for the last 10 years. More than 1,000 wells has been drilled since the start. And using this type of weak symptom detection, so the number of sidetracks, technical sidetracks for those wells has reduced from 30% to 9%. So just to let you know that actually drilling in the North Sea is very complicated because we have a lot of brown fields and quite difficult conditions for drilling. So it's not, that's explained why there are initially quite a lot of sidetracks, technical sidetracks happening. But that has been very seeable impact using this weak symptom detection for taking proactive actions on the reduction of or the improvement of the operations. So, and that's a good sample of data when we are talking about more than 1,000 wells. Now we move to assistance to drilling operations, drilling automations. And the first topic I would like to address is what is called fault detection, isolation, and recovery. And I will not go through all the different types of FDIR and fault detection, isolation, and recovery. I will exemplify them with one, which is the detection of overpulls and set-down weight. So here is a results from two operations. So we see that we are pulling the string. The previous stand, there is nothing happening. Then we pull the next stand, and then we get another pull just after the connection. And then when the driller try to go downward, actually you get a set-down weight. And that's typical conditions when we are getting into a cuttings bed. So can we avoid that? So this is typically what we want to do. The concept has been introduced by Walter Dredd back in 2008 with this, what he called QED, quick event detection, and he was focusing on detection of fluid influxes. But that has been generalized to any kind of abnormal situation for which you would like to react as quickly as possible. And more generally, that is called fault detection, isolation, and recovery. Now, the detection thresholds needs to depend on the context, the current conditions. So you may have some parameters which are changing fast, like the flow rate, like what is the air gap into the drill string, and so on and so forth. And therefore, you need to pass that type of information to the drilling control system so that it can react fast to those abnormal conditions. So what happens is we have a drilling controller, the drilling control system, which is controlling the mud pumps. We have controlling the top drive, controlling the door work, or the hoisting system. There are some set points which are provided. And usually those set points are going directly to the controller. And the controller manipulates the system or manipulate the machines at the surface, and that influence the system. And then we have some measurements which are made. And these measurements are utilized by this current state estimation. So all what I've explained in the previous part, which is this digital twin and the calibration mechanisms. And these calibrated information, these calibrated models are used actually to calculate what are the threshold by which the system should detect that actually there is an abnormal condition. And when there is an abnormal condition which is detected, so the FDIR function switch off actually the set point which is coming externally and replace actually the inputs to the different controllers by its own procedure, which is typically described by a finite state automaton, which will try to isolate the problem in the first place, and then later possibly to recover from the situation. So that's basically this notion of fault detection, isolation, and recovery. So an automatic system which detects an incident and which react immediately to avoid an escalation of the gravity of the situation. And that depends on this current state estimation. Now, the other concept that has been developed is related to safe operating envelopes. So the notion of safe operating envelopes is known for a long time in the aviation. That has been developed back in the 1960s for fighter planes, actually, to make sure that you will not exceed the flying capabilities of the aircraft. But that can also be applied for drilling operations. You see here an animation from true operation where we are pulling the string. We see downhole pressure in ECD as we are pulling the string, and we can see actually how the downhole pressure is below the collapse pressure, which is actually making that the well is collapsing. So the speed by which actually the string should have been manipulated should have been much lower, so that we didn't go below the collapse pressure limit. So that's what we want to do, is to make sure that we have safe operating envelopes which are respected while we are moving the different components, like either the fluid or the drill string, either actually or rotationally. And these safe operating envelopes are, for example, shown here for the axial displacement for swab and surge. They are both values which are corresponding to velocity, but also to accelerations. And there are different types of conditions, whether we are going downwards or upwards, whether we are circulations of fluid or no circulation of fluid, and whether we have gel durations or no gel. So all this can change quite fast, actually, and therefore needs to be updated continuously to adapt to the current drilling conditions. So we add a new layer on this schematic for the control of the drilling operation. The first, the innerst layer was the drilling control system. The next layer was the fault detection, isolation, and recovery functions. And then we have a new one, which is about the safe operating envelopes. The role of the safe operating envelopes is actually to cut actually the set points which are passed actually to the drilling controller. So if the value is too high, then it's actually the value from the safe operating envelopes which is used. If it's vice versa, if it's a minimum value, if it's too low, it would be the safe operating envelope which is used. So that means actually that this can be used also in manual mode. It doesn't need, so both the fault detection, isolation, and recovery and the safe operating envelopes can take any kind of set points, whether they are coming from manual commands from the driller or from an automation system. And that's important. So the placement of those functions into the hierarchy of for the control is very important to allow for protections also in manual modes. Of course, the safe operating envelopes depends on context and therefore depends on all these calibrations and digital twin that we described earlier. And then you have controllers like auto drillers, So the work that we've done is really based on the bit-rock interaction model from Emmanuel de Tournai. This model is based on 3 phases for the functioning of the PDC bit. Phase 1 is directly proportional to the depth of cut, and then there is a boost of performance in phase 2, because actually the friction part of the cuttings is actually not increasing, it's stable, and therefore you can have a larger removal of rock for the wet bit. And then in phase 3, so you are going beyond the thunder point, and then you are starting to increase again the friction part of the cutters on the formations, causing a lower performance of the bit. So the model calculates the estimated ROP, which is shown with these different colors, which are shown here, as a function of the wet bit or torsional speed, and as a function of the flow rate. And it also calculates the constraints that needs to be respected. You don't want to buckle, you don't want to have vibrations, and so on and so forth. So you have those limits which are shown here with these zones indicated here, and that means actually that the auto driller configuration is both trying to maximize the rate of penetration without going into the zone, the phase 3 of the bit, and at the same time respect the constraints that has been given to avoid producing too much cuttings compared to, for example, transport of cuttings, capability of the circulation that you have there. And then the system calibrate the model from Emmanuel de Tournai. There are 7 parameters for this model, and it calculates actually those 7 parameters using a particle filter method. And again, you see that the estimation of those parameters are made also considering the uncertainty on those estimations, which is shown with this bound showing the uncertainty for each of those parameters. Again, uncertainty is a constant problem or constant feature of all what we are doing in what I'm presenting. So, new layer on top of the safe operating envelopes, we have a certain number of constraints. We have an estimator, and then we have the controllers for performing the ROP management. Actually, there are a little bit more things than that, but that's the major part of this one. Then we move to the next topic, which is the standard procedures, which is the last part for the different types of functions. And so standard procedures can be a lot of things. That can be a pump startup, that can be top drive startup, it can be a friction test, which is the one that I take as an example here. And what is interesting to note is actually if you do a friction test by rotating off bottom first and then stopping the rotation, and afterward doing a pickup and then a slack off, you should note that actually the distance by which actually you need to move the bit before the bits move the stop of string before the bits start to move, which is shown in red here, is actually shorter than the distance that you need to move the top of string before the bits start to move in the slack off period. And that means that you need to calculate ahead of time how much you need to displace the block for the whole friction test before you can have actually a true measurement of the slack of weight. And that is quite fundamental. So these standard procedures, they are not simple things. They need to be parameterized compared to the context. This distance depends on the length of the string, the elasticity of the string, the effect of pressure on the string, but also the friction, to know that actually you will perform a good friction test. And that is fundamental for performing good the standard procedures is that the standard procedure should be optimized compared to the current context. So we have a new layer added to this schematic, the control hierarchy, which is now the layer corresponding to the standard procedures. And in the standard procedures are typically described with fine state automata, which are providing actually the commands or the set points to the rest of the control hierarchy. But that means that all the standard procedures are protected by the safe operating envelopes and by the fault detection, isolation, recovery. So if during the friction test there is an overpull, then the fault detection, isolation, or recovery will stop the friction test and start to do proactive actions actually to avoid escalation of the problem that you've got there. So again, this is not only theory, this is not only research, this is actually being used. So this is implemented on actually as of March on 28 rigs in the North Sea, and that will be implemented on 34 rigs in the North Sea by the end of 2025. And I think by the end of 2026, almost all the floating rigs in the North Sea will be equipped with that type of technology, which shows actually that this is used every day in the North Sea. And now we can finally go to autonomous training. And I'd like first to start with the notion of taxonomies for training automation. So John DeWaart, when he worked on the SP training automation roadmap, has used the classification that has been developed by Luca Save and Beatrice Feuerberg. And he came with that particular setup for the classification of automation system. And one characteristic of this classification for automation is that actually it says in a way if there is no human intervention, it's fully automated. And that's okay. But that doesn't mean that this is actually autonomous. Autonomy is something different from automation, and that's what I would like to argue. So together with John DeWaart and with Rodica Mihai and John McPherson and Dimitrios Spirovoulou, so we worked on how can we classify or what would be a system which is an autonomous system. And we came with all this list of different threats that an autonomous system should have to be qualified to be an autonomous system. And this is very different from simple automation. Basically, what those threats says is that actually the system has a goal, it's adaptable, it perceives its environment, it makes decisions, it takes actions, it learns from experience, it has strategic and tactical abilities, it is independent, it can collaborate, it is self-contained, and so on and so forth. So you see that these things are not necessarily what you can do in classical cybernetic world. It's at a much higher level. It's more AI oriented type of ways of thinking. And we put together a way to display whether a system is whether it classifies to be autonomous or not using this radar plot where we have some of those major threats which are put there, and the minimum requirements is shown by this red region here for each of those things, and the maximum score you can get is 8. And if a system like the gray one, which is shown here, is not crossing any of those red lines, then it can say it's an autonomous system. But if it score good in many of those, but cross one of those red lines, actually it is not an autonomous system. So it needs actually all those features, all those traits actually to be able to be qualified for autonomous system. So I would say that the big difference between automation and autonomy is basically that automation corresponds to what happens in the spine. You have a lot of functions of the body which is managed by the spine. This is automatic functioning, the breathing and the heartbeats and all these kind of things. But autonomy has to do with the brain. There is a need for having a goal. There is a need for taking decisions, which is not at all what is at the level of those automation systems. So how can we achieve that kind of autonomous system? Well, as I said, so it needs to take decisions, and take these decisions, it needs to do something which is, first of all, to be performant, drill fast, shorten the weight-to-weight procedure, quick pipe handling, and at the same time balance with the risk. We want to avoid vibrations, we want to avoid pack-offs, formation fracturing, and so on and so forth. So it is really a problem of a multi-objective optimization problem. And the way we try to solve that is to say, okay, actually we can represent that balance between performance and risk through the time to reach section TD. If we minimize the estimated time to reach a section TD, so we are both performant and manage the risk. And this time to reach a section TD is a sum of the time for each of those actions that we are planning dynamically, and also the cost of any incidents which can come, which is associated with probability distributions, and also the cost of solving the problems caused by the incidents. So by solving that, so we can actually have a system which can take decisions. And the way it works is actually that we use again this estimation of the drain conditions using the weak symptoms that I've described in the first part or the second part of the presentation. And then we estimate the probability for different description which can take the risk. And then we estimate, based on those probability for these descriptions, what would be the consequences for the time to reach a section TD. And the method which is used to solve that is using an algorithm which is called the Markov decision process, which estimate at every change of state of the system what is the action which will optimize actually the time for reaching the section TD, both in terms and that account for the short term, medium term, and long term. So it's a multi-time horizon estimation of the decision, and that means that the system can take actions which looks like it, on the short term tends to decrease the performance, but which can have a positive effect on the long term because you may just avoid some escalation of downhole deteriorations while you are operating. So going back to this hierarchical control that I've explained, so we have the final level, which is the autonomy orchestrator, which is taking the current state estimation, which is doing this performance analysis and risk analysis, and takes decisions and decide on which of those functions which are available, or which of those standard procedures which are available to activate and to drill the well. And this is not only theory that has been tested on a test rig that we have here in Norway called Ullrigg. You see here a movie of this operation. So we drilled 500 meters completely autonomously on Ullrigg, where all the decisions, all the actions were made by the autonomous system. You may note that our driller, Arild, doesn't touch anything. He doesn't have the hand on the joystick, doesn't manipulate the keypads. And you will see, that the system has taken a decision to make a reciprocation because there is a poor cuttings transport. And therefore, it has decided actually in the middle of this stand to try to lift up all those cuttings because they were starting to accumulate around the BHA. So just there, you see that the reciprocation has started. And this is not decided by Arild, it is actually decided by the system itself. So that shows actually this kind of autonomous system. So now finally I've got to the conclusion. Sorry for taking so much time. What I want to highlight is that there is a lot of transient effects. It's important to account for them. It's important actually to estimate the internal state of the system, which is very poorly observed by the sensors. But at the same time, we need to model how the sensors are working because they never measure actually what we want to measure, which is the true state of the internal state of the system. We need to account for uncertainties, both modeling uncertainties and measurement uncertainties. And this is actually the most crucial point, actually, to be able to either detect weak symptoms, but also configure automation systems and also to guide autonomous decision making. And it's also important to have protection systems, protection functions like the full detection, isolation, recovery, the safe operating envelopes, and also that the automated drilling procedure needs to adapt themselves to the current downhole conditions. They are not statically defined because the context change continuously. And finally, so autonomy is about making decisions toward the goal and learning from experience. And this is quite a different level than automation. And thank you for listening. So now we can talk more.
Eric, thank you so much for bringing and doing a full lecture today.
Sorry about that.
No. This is what the show is for. Is to be. I mean, I know SPE is not going to allow us to do this. So somebody's got to be able to put these opportunities out there. Hopefully, for everybody that's still watching, hopefully you guys got a lot out of that. If y'all do have any questions, throw them up there pretty quick. But I'm absolutely thrilled with this today. So I won't keep anybody much longer. And like I said, Eric, you did an amazing job today. So if anybody's has any questions, go ahead and throw them up there. Then what we'll do in the meantime, we'll add this to the stage. Like I said, today's show was brought to you by Ullrigg Reports. So Phil Harbridge, he did it right. Put in hashtag Ullrigg Reports. So we'll go ahead and do the drawing here. Let's see if anybody else get our winner is today. Sandeep. All right. There we go. You are the winner of the day. He was also the one that had the question about the available models. All right. So go ahead and take that. Sandeep, we'll go ahead and get you a drill bit and name placard sent over to you, courtesy of Ullrigg Reports. And we did get a question here. Robin's still tuned in. It says, hi, Eric. Does the system on Ullrigg announce a decision to act and explain why?
Excellent question. So that actually not. So that was a test which was made in a research project. And that's what we saw actually, that actually the weakness of the system we developed was actually the system was taking decisions but didn't inform the driller. So we are working on changing that. It's important actually, this communication with the driller, to explain what, or to tell about the decisions that will be made in the very near future and the reason why it makes these decisions, and gives the opportunity for the driller to say, well, I don't want to execute that decision or not. And actually, we are planning a test of this revised version on Ullrigg, on this test rig at the end of 2025. And then with the goal, if it's successful, to test that on a rig offshore Norway during a true operation. So, but this explainability of the system is very central actually for acceptance and for safety also, because we never know whether the system can maybe do things which is, or propose things which is not completely logical compared to the overall operation, because the system cannot have cannot oversee everything that is happening on the rig. But excellent question, yes.
Here's another one. I saw somewhere that OpenLab app may be discontinued by the end of this year. Could you please confirm if this
No, I don't think so. No, no.
Right.
That's for sure that it's still there and it will continue like that. It's just to say it's qualified as a national infrastructure in Norway. So it will be there for a lot of time.
Excellent. Well, good news for all of us there. All right. And then compliments from John Doerr. Excellent presentation as usual from Eric. Thanks for putting it together. Yes, we do appreciate it. All right, guys. That's it for today's show. Thank you guys so much for tuning in. Do appreciate it. Thank you to Rig Reports for sponsoring today's show. Like I said, won't be back next week. We'll have something the week after that. I'll make sure that we continue to keep having people lined up. If you do know somebody that you think would be amazing to have on the show, tag them in the comment section or send me a message. We'd love to be able to get them on. That's it for me. As always, guys, know your industry.